Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in to this video on the factor and remainder theorems. So what the factor theorem is stated on the screen. We're just going to come back to that in a second. First, let's look at what's motivating us. So remember when we were solving things like x squared minus 6x plus 8 equals 0. What we did was we factorized this. We found two numbers that multiply to positive 8 and add to negative 6. So when we did that, solving it was easy. We just used the null factor law, x equals 2 or 4. Okay, how easy is that? But what about if we want to solve polynomial equations where the polynomial has a higher degree than 2? So solving this polynomial in black is not an easy task. Now, unlike for quadratics, we can't just find, two numbers that multiply to this and add to one of the other coefficients. Unfortunately, it doesn't work like that. Now, because this is a degree 4 polynomial, there are up to 4 linear factors and 4 possible solutions for x. But we want to do what we did over here anyway. We want to find up to 4 linear factors and then use the null factor law. So I want to be able to factorize this polynomial by filling up each of these brackets. So each of these brackets I want to be a linear factor. I want it to be of the form x minus a, so then this will be easy to solve. So the factor theorem tells us how we can find these linear factors. What we do is we need to find a value a that I can substitute for x that solves this equation, and then I can take the negative of that and use it as a linear factor. So we're sort of doing the opposite of what we're doing with quadratics. Here, we're actually finding the solutions first and then factorizing. So what we actually have to do, it's kind of a bit annoying. We have to use a bit of trial and error, but we're going to take some educated guesses. Now, the rational root theorem tells us that any root of this polynomial will be a factor of the constant term, but you need to try positive and negative factors of 6. So in case you don't know what a root is precisely this, a value a that makes the polynomial equal 0. A root of this polynomial is a number I can substitute for x to make it equal to 0. So what the rational root theorem says is that those roots, those numbers that I'm looking for, if they're rational, they will be positive or negative factors of 6. So I'll just digress for a moment and say sometimes you can get a polynomial and its roots, the values of x that make it equal 0, they can be weird things like 1 plus square root of 2. They can be like, 3 minus the cubed root of 13. So we're not going to go through those. In that case, you just get a computer to factorize this for you. We're just looking at cases where all the roots are rational, or in this case, integers. So what we're going to do is we're going to try, in order to factorize this polynomial into full linear factors, we're going to try positive and negative factors of 6. So if I call this polynomial fx, let's try some. So let's try, for example, f of 1. If I substitute x for 1, I get 1 to the power of 4 minus 1 cubed minus 7 times 1 squared. And if you put this on your calculator, you end up getting 0. F of 1 is 0. So that means that x minus 1 is one of the factors. So let's try other positive and negative factors of 6. Well, I tried 1. Let's try negative 1. So I get negative 1 to the power of 4, and so on. Of course, negative 1 to the power of 4 is positive 1. Negative 1 cubed is minus 1. So I get 1 minus minus 1, which gives me 1. So negative 1 squared is positive 1. And then I have another negative 1 and a positive 6. And once again, this is equal to 0. So that means that x minus minus 1 or x plus 1 is also a linear factor. So let's try x equals 2. So if I try x equals 2, I just substitute that value for x. So this is what happens when I substitute x for 2. Now, if I put that in my calculator, this time I don't get 0. I actually get minus 12. So that didn't work, but that means x minus 2 is not a linear factor. So let's try f of minus 2. So here I would get minus 2 to the power of 4 is positive 16, so negative 2 to the power of 3 is minus 8. Then I get minus 7 times, so negative 2 squared is positive 4, minus 2 plus 6. Put that on your calculator, you get 0. So that means that x plus 2 is a factor. X minus 2 is not a factor, but x plus 2 is a factor. So when you've got all but one of them, you can figure out the last one easily. So think about it. If I were to expand this, what will happen is I get x plus some number. When I expand this, the final term, the constant term, will be minus 1 times 2 times whatever's in the box. So minus 1 times 1 is negative 1, times 2 is negative 2. So what goes in this box here is what do you times by negative 2 to get this number here, positive 6. So that is, of course, negative 3. So that means that the final factor will be x minus 3. Again, why is it minus 3? Because minus 3 times 2 times 1 times negative 1 gives you positive 6. So now I've factorized this. I know what all the solutions are. I have x equals 1, x equals minus 1, x equals minus 2, x equals positive 3, and I'm done. So we used the factor theorem here because we found values that made the polynomial equal 0, and then x minus that value was a linear factor. So let's go on and look at the remainder theorem. So the remainder theorem is all about when we want to divide polynomials. So let's say we want to perform this division here, x cubed plus x squared plus 1 over x plus 4. So what we're really saying is we want to take x plus 4 and we want to times it by some polynomial to get x cubed plus x squared plus 1. But we won't always be able to find a polynomial that we can insert here that will give us this answer here. Because x plus 4 is not always going to be a factor of this polynomial. In fact, we know that x plus 4 won't be a factor. We can use the factor theorem. So we know that if I let's call it gx, if I let that equal x cubed plus x squared plus 1, if I take g of minus 4, I get minus 64, so that's minus 4 cubed plus 16 plus 1. That clearly doesn't equal 0. That equals minus 47. So the factor theorem tells us that because g of minus 4 does not equal 0, this is not a factor of that. So what am I going to do then? Well, what I can do, instead of finding a polynomial that can multiply by x plus 4 exactly to get this, find a polynomial to put here so that when I expand them, all the terms with x's are correct, but this number at the end might be a little different. So it turns out I can if I times x plus 4 by x squared minus 3x plus 12. If I expand this, I get this. So this is just using polynomial expansions, expanding the brackets like we did last lesson. So timesing x by the first brackets gives me this, and then I multiply 4 by the second bracket to get this. Now I collect like terms to give me this. So what essentially I found is I found the best possible polynomial I can multiply by this to get near this. Because if I multiply these two together, notice that x cubed and x squared, the x terms are right, but the number I get here is a little different. As you can see, if I want this polynomial to equal this one, I also need to subtract 47, and that's exactly the number I got here. And that's what the remainder theorem is saying. When I take a polynomial here and divide by a linear term, the remainder that I will get is equal to the number when I substitute the negative of this into the polynomial. So here, a was like minus 4. So this is x minus minus 4. So the remainder, when I divide this by this, is just if I substitute minus 4 into this polynomial. And what this will allow us to do is do division with a remainder. We will be able to divide two polynomials even if one is not a factor of the other. So this goes hand in hand with the factor theorem. In fact, they both imply each other. So of course, if the linear term is a factor of a polynomial, the remainder will be 0. That's what the factor theorem told us. And we know this. Something is a factor of something if there is a 0 remainder. We know 4 is a factor of 36 because when you divide 36 by 4, there is a 0 remainder. So that's the same with polynomials. This polynomial is only a factor of this if there is a 0 remainder. If there's not a 0 remainder, as we found here, then that means that x plus 4 is not a factor of the polynomial, and there will be a remainder. The remainder theorem tells us how to calculate that remainder, just like we did there. All right, let's just do a couple more questions now where we're finding one of the coefficients. So let's look at this question here. The remainder when x to the power of 4 plus kx squared minus 5 is divided by x minus 2, the remainder is 3. What's the value of k? So let's let fx equal the polynomial x to the power of 4 plus kx squared minus 5. So let's think about what the remainder theorem says. What it says is when I divide this by x minus 2, the remainder will be f of 2. So of course here a is 2 when we were talking about, the linear factor x minus a. So f of 2, if I substitute x for 2, I get 2 to the power of 4 is 16 plus 2 squared times k, so 2 squared is 4. I get this, or 11 plus 4k. Now we were told that the remainder is 3. So that means f of 2 must be 3. That means 11 plus 4k must be equal to 3. Subtract 11 from both sides. Divide -8 by 4. You get -2. So that is the value of k. So what is this actually saying? So this is saying if I take x to the power of 4 minus 2x squared minus 5 and I divide it by x minus 2, the remainder will be 3. It means if I take x minus 2, I can find some polynomial that will get me close to this polynomial here. So because the remainder is 3, it'll give me x minus 2x. It'll give me the x terms, right? But it won't give me the constant term. So I can actually, turns out, find a polynomial here that will get me to x squared minus 2x minus 8. Because the remainder is 3. I'll need 3 more to get here. So finding this polynomial here is what we're going to do when we do polynomial long division in a subsequent lesson. But that's what's going on here. We can't multiply x minus 2 by a polynomial to get this one exactly, but we can multiply it by some polynomial to get it very close to that. All right, thank you so much for watching this video. This has been the luckiest maths teacher in the world. Have a great day.